So we come to page 69 and the method of virtual work. Virtual work here in Chinese is this one. If you go to read books in Chinese, that the Chinese name of this one is virtual work. This one, and it sounds new, but you have learned some parts of this chapter. Work is in physics or in mechanics. Work is this one. Okay. So work W. In physics, what have you learned about W? Work. Work is equals to what times what? How do we define one? Two. 1 Newton, we exert 1 Newton of force by 1 meter. So it is F dot S. Remember, and in this, of course, we know force is a vector, but work is a scalar, and it has no direction. Okay, work is a scalar. So work is scalar, and work is not a vector. So sometimes we use work to we use this to do our to work out some problems because we don't need to consider x direction, y direction, and z direction, and we only need to consider a scalar. Is that okay? F dot S. And remember, and in this course, work is the direction of force and direction of displacement. They don't need to be in the same direction. So we can have F dot dr. We can do work it out this one. Okay. F dot dr would be equal to F times dr times cosine alpha. They don't need to be in the same direction. They can be in different directions. So, and in this chapter, we work on something called this is called virtual work. And in this week, I mean in this half an hour and on Thursday, probably next week, and we always work on this one called principle of virtual work. In Chinese is this one. Now, and virtual displacement, and let's have before I talk about this principle, because principle is principle is and the virtual work is. Let's talk about the difference between virtual displacement and differential displacement. and they have different symbols. And this one is delta R, and another one is dr. Now, as let's say S is displaced, let's talk about something we learned at high school. If S is displacement, of course you can answer in Chinese. Now, if S is displacement, so what is the change of displacement over time? What is that? What is the change of displacement over time? Okay, good. Oh, actually, sorry, actually. Wait a minute. And let me. How where should I write it? And can I write this? And what is the change of velocity? This velocity. Velocity. What's the change of velocity over time? Okay, good. So change of velocity over time is acceleration. And in so that is what you learned in high school, right? Displacement and change of displacement over time is velocity. Change of velocity over time is acceleration. In next year, you will learn one more, and the change of acceleration over time is yeah. And in Chinese it's like this, but in in English it's just. So it's change of acceleration over time. And for example, if you go on the metro and go on taking a train, so if this one describes how comfortable it is. Okay, this one. So we have displacement, we have velocity, we have acceleration, we have jerk. And of course, we know F equals to ma, right? And for, uh, and you will learn this in dynamics. Now, for these four quantities, for these four things, it actually exists. Okay, if you drive a car or you take a train, it exists. And for this s ds dt d square s dt square d cube s dt cube, this is square and this is cube, right? Uh, power 2 is square and power 3 is cube. This quantities actually exist when you drive a car or take a train. And for F equals to MA, that one of this is the cause and one of this is the result. So most of the time we have a cause because we have force, and then we have results, right? There is a relationship we call causation or cause. I think I would say causation. Sorry. Okay. If we say F equals to MA, then most of the time at high school, that because we have a force and then we have acceleration, right? Can we say this? So we would say this is a causal relationship between F and A. And this is what we have learned in high school, except, of course, except this one. But most of them, we have learned this at high school. And of course, we know dr is small, right? This one is small. And actually, this one is also small. After we talk about the right-hand side, let's talk about the left-hand side about virtual displacement. Virtual displacement is also small, but we will talk about what happens if it exists, okay? What happens if it exists? But in reality, it does not happen. It's okay. In I think on Thursday or next Tuesday, we will talk about this virtual displacement. Virtual displacement does not exist in reality, but we talk about what happens if it exists. It's okay. It's different from the right hand side. For the right hand side, if you drive a car, if you take a train or take a bus or a coach, it exists because we have displacement, we have velocity, we have acceleration, we have jerk. But on the left, we talk about something if it exists and it does not happen in reality. That's the first thing. The second thing, let's take a look of this part, this mass A. Now, and suppose it has three forces acting on mass A, on point A. And then we consider one virtual displacement. It does not occur, but it does not happen in reality, but if it exists, okay? That's from A to A prime delta R. This is virtual displacement. So we have these three forces and we have one virtual displacement. Are we talking about having these three forces would make it move from A to A prime? The answer is no. Okay. Because we have three forces here, and we have one virtual displacement here. You may ask, oh, are these three forces lead to displacement here? The answer is no, because there is no causal relationship between F and delta R. Okay. And we just say what happens if it moves from A to A prime. But there is no cause and results between F and delta R. We are not saying because we have F, so therefore we have R. Okay, because we are not saying because there's F and we have delta R. We are only saying that there is F and there is delta R, and these two have no relationship. Now, let's take a look of, but nevertheless, and nevertheless, if we have a force F and we have a displacement delta R, we can calculate a work, right? This is called virtual work. It's okay. Because we have a force, we have a displacement. Okay, a virtual one. That's it does not happen in reality, but let's say we have one. And we have a force, we have a displacement. Of course, we can get a work because we can multiply these together. And this is called virtual work because this is virtual displacement. Now, and let's consider any mass like having three forces acting on it. Say F1 uh, F2 and F3. Let's say. Let's say we have a particle, and we have three forces acting on it, and suppose it has a virtual displacement going this way. Suppose, or if there is a virtual displacement. And we can get we can write down the total virtual work due to because we have this displacement, right? We have force time displacement, force time displacement, force time displacement. And we can add these three together because it is a scalar. And because this one can become this one. So what do we know if the particle is in equilibrium? If the particle is in equilibrium, we know that. What do we know about these three adding together if it is in equilibrium? Summation F equal to 0. Therefore, because we have 0 times something, so we will have summation delta W equals to 0 if particle is in equilibrium. And this is the principal virtual work. And I'll talk more about this on Thursday.